everyone, and let me check whether the okay, yeah. Hello everyone, good afternoon, and welcome to today's class for bioelectrochemistry. As you know, this was a 4-week course. So today marks the last class for our particular subject. I hope you guys are up to date with respect to the syllabus and the content which are covered in the lectures, and most of you are engaged or say registered for the exam. It's a good course and it will be nice on your transcripts also. So we can quickly go and start our discussion about today. Let me choose the laser pointer. I hope every one of you can see my screen. So before beginning of today's class, we'll read something about mitochondria and electron transport chain. If you guys are not from the biological background, you might not have heard about it, but if you are from biological background, you have little bit or basically most of the idea about electron transport chain and why it is paired with mitochondria here. So in biology, we why do we eat food, right? We eat food so that we can get the energy out of it. How do we get the energy out of it? By breaking the bonds from the complex molecules, breaking them down to simpler molecules, then at the end breaking those bonds, and at the end of the day taking that energy, right, which was stored in the form of chemical bond, will be broken down, and we can use that energy for our various functions. At the end of the day, you know that breaking a bond also requires energy, but where that energy comes from? Okay, that energy comes in the form of ATP, adenosine triphosphate molecule. Okay, that ATP needs to be there to make sure that we have enough ATPs, or say energy currency, to do some work. Okay, now how does this ATP is produced in us? There has to be a site, right? So we started to discuss about cell, then membrane, and then there are different organelles inside it, right? So one of the organelle is mitochondria. So in mitochondria, a process called electron transport chain occurs, which makes the ATP, or the energy currency. If this organelle is not there, or say electron transport chain doesn't exist, we won't be able to have enough ATPs to do our work. So do you remember, like whenever you feel very low on energy, we generally have glucon D things or glucose, or people suggest us to eat something, right? So people tell us to eat something. So why do we need to eat when we are feeling low on energy? It's because the reservoir for energy, that is ATP in human body, is reduced. To replenish it, we need to have some sort of food, so that the energy which is stored and that food in the form of chemical bonds can be broken down for us to be converted into ATP, so that this ATP can be used as an energy source for our body. Okay, hence mitochondria and electron transport chain are very important for us to do function of any sort, okay, work. So since the beginning of this particular course, we are studying now that work has to be done on the system or by the system. So how it is being done? By electricity, the flow of electrons. How those electrons are being formed? By chemical reactions, correct? So everything is linked. Similarly, if we talk about biological system, in mitochondria, which is called the powerhouse of the cell, which is called the powerhouse of the cell. Why it is called the powerhouse of the cell? Because the process of electron transport chain occurs in mitochondria, right? So mitochondria are double membraned organelles found in eukaryotic cells, responsible for aerobic respiration and ATP production. As I've told you, what ATP is? ATP is adenosine triphosphate. So what the name suggests, triphosphate, it means it has three phosphates. meaning it will be having 3 phosphate groups attached to the adenosine molecule. When we need energy, these phosphate bonds are broken and the energy is released for the work to be done, depending upon whatever work is required at that time. Okay. So mitochondria are double membraned organelles found in eukaryotic cells, responsible for aerobic respiration and ATP production. Their inner membrane houses the electron transport chain, or ETC in short, the final stage of cellular respiration. So if you guys are not from the biology background, so cellular respiration means respiration process has 2 phases: breathing and respiration. Okay, so breathing is when we take air inside and exhale CO2 outside. Okay, that is breathing phase. Respiration means when the air which we have taken inside, inhaled inside, that air gets into our lungs. From lungs, the oxygen, or mostly it's oxygen only, oxygen gets dissolved into the blood. That blood gets circulated throughout our body. Then the body, again, body are made up of tissue at the end are made up of cells. So when blood is being circulated with oxygen in it, that oxygen gets dissolved inside the cell, it goes inside the cell, and the process of respiration occurs inside the cell. The respiration here means making of the ATP or breaking of the ATP for different functions. Okay, so some key features of mitochondria include outer membrane, inner membrane. So mitochondria is one of the double membrane organelle. Okay, so the outer membrane is permeable to ions and small molecules, while inner membrane is highly folded into cristae where the ETC takes place. So if you remember that this differential movement of ions or selective permeability of membrane is required to maintain a potential difference, right? This phenomena is only used in the electrochemical cell also, right? The galvanic cell which we studied in the first week. The galvanic cell is what? It is the creation of the potential difference. And how it is being created? It is being created by the chemical reaction which is spontaneously occurring because of the difference in the redox potential of the compounds which we are using. So at the end, the aim is to maintain a potential difference. Here in living system, that potential difference is maintained by the ability of the membrane to allow some of the ions to come inside it and vice versa. So this selectivity of the membrane for certain ions and not allowing other ions to cross through it maintains the differential concentration of ions across the membrane, and wherever there is differential concentration of ions, the voltage or the potential difference will be generated. Okay, so if you remember our last week's discussion, the resting membrane potential for a neuron is minus 70 millivolt. Okay, indicating that inside of our cell is minus 70. It is 70 times negative concentration of ions is more inside in comparison to the outside of the membrane or the lattice in which the cell is connected, not the internal part of the cell. Second is the inner membrane, where this particular process takes place. The process which we are talking about is called electron transport chain. And then the matrix that contains all the enzymes, because at the end of the day, if a process is taking place, complex molecules are broken down into simpler ones. We need enzymes which can increase the rate of reaction without being consumed. Okay, then the second part is the electron transport chain. The ETC or electron transport chain is the final step in aerobic respiration, located in the inner mitochondrial membrane. It consists of 4 protein complexes. The names are like complex 1 to 4 and the ATP synthase. Okay, these are the complexes of the ETC. So we're not going to go too deep into it, but as I mentioned, where the ETC takes place, electron transport chain takes place, it's a series of reactions at the end of the day. If I want you guys to take away this one particular message, it will be, so in mitochondria, which is a double membrane organelle, in the inner membrane of it, ETC occurs. The components of ETC are enzymes which are present in the membrane. So there are four enzymes and one ATP synthase at the end of the whole process. Okay. So the basic steps which are there in the ETC are electron donation. So now you can see, right, that why ETC important and why we are discussing it in a chapter of bioelectrochemistry, because there has to be a transfer of electron, as the name suggests, electron transport chain, and wherever there is electron transportation there has to be a maintenance of potential difference, and hence we are studying about how that electron is being transported in this chain. So till now what we are aware of, that this chain has four enzyme complexes named as complex 1, 2, 3 and 4, and there is another enzyme associated with it which is called ATP synthase, and these are the part of electron transport chain. So the first step is the donation of electrons from NADH and FADH2. So here the electrons are transferred from NADH and FADH produced in the Krebs cycle to complex 1 NADH dehydrogenase and complex 2 succinate dehydrogenase. Basically what it means that, so for electrons to be transferred from one enzyme to another enzyme, there has to be some small molecules which can carry them with themselves, get to these complexes, and then due to the difference in the reduction potential they'll be able to donate the electrons, right? This is how we have read, we have studied about the galvanic cell also. So this is the same principle is also happening here. So the complex one, which is called the NADH dehydrogenase, here it receives the transfer of electrons from NADH to the ubiquinone Q and pumps protons. Don't go into too deep with respect to this. This is just an important process which occurs in cells to generate ATP, and I have told you the ATP is important, but with respect to this particular subject we don't need to know the details of it. It's just you should have a basic understanding and knowledge about ETC. Okay. So the first complex, it is saying that the electrons are transferred to this complex from NADH and FADH. These are small molecules which can transfer electrons. Okay. Then electron transport and proton pumping. Now why proton pumping is there? As I mentioned that for the transportation of electron, what is required? Potential difference is required. How can we generate potential difference? By differential concentration of ions. Okay. Here the ion which we are talking about, which should be differentially located across the membrane, is hydrogen. To maintain this, that there is a difference of hydrogen concentration inside the mitochondrial matrix and into the space between these two membranes, a pump works. Okay. So that this difference is maintained and electrons can transfer from complex 1 to 2, 3, 4 and at the end to the ATP synthase. This is the whole process. So now you understand that if any of these complexes, imagine, stopped functioning, let's say there is some issue in the complex 1. So what is complex 1? Complex 1, all of these are just enzymes, right, which are present in the membrane. So in the last class we discussed about the functions of proteins which are present in the membrane, right? We studied that, correct? That the membrane contains lipids, they have proteins, proteins have different function, and one of the function of these protein was to act as an enzyme. So we are talking about those enzymes only. So ETS is a process which is made up of four complexes and ATP synthase. These complexes are proteins at the end of the day. Now imagine some mutation has happened, right? And we don't know what is that mutation, but imagine because of that mutation complex 2 stopped functioning, right? Meaning that you have a healthy cell, you have a mitochondria, the mitochondria has all these complexes and ATP synthase, but the complex 2 is not functioning. It is not able to accept electrons, because at the end of the day what all these complexes are doing, they are accepting electrons. So anyone of you would like to guess what will happen if complex 2 is not working due to a particular, due to any
Good
issue?
evening, ma'am.
Yeah, hi. Hello.
Ma'am, am I audible?
Yeah, yeah, you are audible. If I'm correct, you are Rajeshwari, right? Hello, can you hear me? Hello, hello.
Hello, ma'am.
Yeah, Rajeshwari, I can hear you. Can you hear me? Oh, okay, okay. I guess I was muted since long, right? Yeah, 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 it's okay. Oh, don't worry, I can repeat myself. I forgot to like unmute myself.
Yes, ma'am.
You could have texted me earlier. It's okay.
Ma'am, actually, I thought no other participants were there.
Yeah, yeah,
So
got it, got it.
whether you are waiting for others or I think so.
It's okay, it's okay. It was my mistake. I'm so sorry. Yeah,
Yes, ma'am.
so till now, what I was discussing is about the concept of mitochondria and electron transport chain. Okay, so electron transport chain, as the name suggests, that's a chain which transports electron. So since the beginning of this particular subject, we are understanding that we need to have a electron transport. And when does the electron transport occurs? It occurs whenever there is difference in the potential difference, right? Whenever there is some potential difference associated with it. In the galvanic cell, the spontaneous chemical reaction was happening, the electrons were generated, and those electrons were transferred due to the potential difference. But in biological system, what happens? When we start discussing about this topic with respect to biological system, we need to know about mitochondria and electron transport chain. So, the mitochondria is an organelle in the cell at the end of the day. This is very basic. Okay. But what does this organelle do? So, this organelle is called the powerhouse of the cell. Okay. So, the mitochondria are double membraned organelles found in eukaryotic cells responsible for aerobic respiration and ATP production. Their inner membrane houses the electron transport chain and final stages of cellular respiration. So, let me decode some of the terminologies which are used here. So, mitochondria are double membrane organelles. So, what do we mean by double membrane? If you remember in the last class, we discussed about the biological membrane, what it is made up of, and what other things it has in it. Okay, so a membrane or a cell membrane is a lipid bilayer in which proteins are present. These proteins can be of can perform different functions and can be either passing the whole membrane or can be just attached to one side of the membrane. Okay, but this was just one membrane, one single cell membrane, and these are the components which we discussed. So a mitochondria is a are a double membrane organelles, which means same membrane which we discussed, this particular organelle will be having two of it. So the first membrane will be like the normal one, the second membrane will also be like a regular one. It's just there is little bit differential amount of proteins present. Okay, so membrane is there, basic components are there, it's just there will be little bit of differences in the lipids and the proteins. So in mitochondria, electron transport chain occurs. So why do we need electron transport chain? At the end of the day, what do we need? Since the beginning of this subject, we are talking about work done. Okay, that work has to be done on the system or by the system. Imagine we are here. You are sitting in the class, you are actively listening, you are doing this work. For the work, you need energy, right? Or voltage, or wattage, or power. Okay, all these terms are somehow synonymous sometimes in this context. So, in this case, from where that energy is coming from? That energy is coming from the food. But whatever we eat, do you think that it is just like this and it is consumed in the form, in whichever form we are having it, and we are getting the energy? No, right? So the process of respiration, digestion, all these processes, what they do is they break down the complex molecules into simpler ones. At the end, these simpler compounds are further broken down, or say that their chemical bond is broken, so that particular energy is released. That released energy is converted to the work which we are doing. Okay, but we need energy. So for us, the energetic term or the energy currency of living being is called ATP, or say adenosine triphosphate. As the name suggests, triphosphate, meaning it has 4 phosphates attached to it. Okay, so whenever we need energy, one phosphate will be broken down, energy will be released, and we'll do the work whichever we want. Okay, but where is this ATP formed? This ATP is formed only in one organelle in our body, in our cells, and it is called mitochondria. Okay, so if mitochondria is not there, we'll be having very low energy, and mostly we won't be able to work at all. Okay, because we won't have any energy to do the work. And where that energy is being formed? That energy is formed at the mitochondria. That energy is formed by which process? It is called electron transport chain. Okay, so some of the key features of mitochondria is, as I mentioned, that it's a double membraned organelle. So outer membrane and inner membrane. Outer membrane is permeable to ions and small molecules. Now connect the same concept to the galvanic cell. So in the galvanic cell, what was necessary? The necessary thing was to choose the electrodes in such a way that they have different reduction potentials, so that electrons can be released and can be accepted simultaneously. Same thing is present here. Due to the semi-permeable nature of the membrane, of the living membrane or cell membrane, there is differential distribution of ions. This differential distribution of ions leads to the maintenance of a potential difference. If you remember the last class, we studied that the resting membrane potential of a neuron is minus 70 millivolts, which means that inside of a cell or a neuronal cell is minus 70 times more negative, or say minus 70 millivolt times more negative in comparison to the outside of the cell, in layman's term. Okay, the inner membrane, on the contrary, is highly folded into cristae, where the ETC takes place, or the electron transport chain takes place, and the matrix, which is the cytoplasm of the mitochondria. Okay, and then the electron transport chain itself. So what is electron transport chain? Electron transport chain is the final step in aerobic respiration, located in the inner mitochondrial membrane. It consists of 4 protein complexes, 1 to 4, and ATP synthase. So what exactly it is? If you remember the last class, so we saw the membrane. Membrane had proteins. These proteins had different function. Few functions were transportation. The other function was to act as a receptor. Another function was to act as an antigen. One function among them was to act as an enzymes. Okay. So if we connect all the lectures, mitochondria is an organelle. It has 2 membrane. The second membrane has these enzymes or proteins which make up the electron transport chain, which means there has to be multiple enzymes in the chain form through which the electron can transfer. Okay, and what are these 4 proteins? These are named as complex 1 to 4 and ATP synthase. Okay, we do not need to know the complete detail of the ETC, but it is like it's good to know the process which occurs in cells to get the energy, because this phenomena works exactly how we do generate the transfer of electricity via the galvanic cell or the spontaneous chemical reactions. Okay, so these are the basic steps which are there in the ETC. The components of the ETC, as I mentioned earlier, are the 4 enzymes which are named as 1, 2, 3 and 4, and another enzyme called ATP synthase. Right, these are the enzymes associated with the ETC chain. Now we'll discuss very basic steps. Just remember your basics and the phenomena which we are focusing here. So the first step will be electron donation. Now for the transfer of electrons, there has to be presence of electron. Electron cannot be freely revolving in the living cell, right? It cannot be there, because otherwise it will create damage to the machinery which is present in the cell, right? So it has to be taken by a small molecule which has a reduction potential, so that whenever it goes to a complex, say 1 here, it will transfer that electron. Okay, so what will happen? The first step is the electron donation from NADH and FADH2. Let's just have this in mind, that NADH and FADH2 are small molecules which carry the electron from the place where they are formed to the first complex or first enzyme of the ETC. Okay, and the first complex is named as NADH dehydrogenase, which basically transfers electron from NADH to ubiquinone and pumps proton. Don't need to worry about all these things, just have in mind that the first complex, it will receive electron from NADH. Okay, the second complex or the second step in the ETC is the electron transport and proton pumping. So if you remember, we are saying that there has to be a differential distribution of ions, correct? Here we are specifically talking about hydrogen ion or proton. So to maintain this gradient, because this gradient is important for the electron to get transferred from complex 1 to 2 to 3 to 4 and finally be converted into an ATP molecule. For this, the second step includes that electron which was transferred from NADH to complex 1 and FADH to complex 2, these electrons together go to complex 3 and to complex 4. Once they reach complex 4, like from 1 to 2 to 3 to 4, they release the energy to pump the proton into the space between these two membranes, creating a gradient. Now this gradient will help in maintaining the potential difference. The third step of the electron transport chain is at complex 4, which is called cytochrome C oxidase. Electrons combine with oxygen and proton to form water. This is why oxygen is essential for respiration. So when we are breathing, we are taking in air. We say that we need oxygen, or we need air, right? So where that oxygen is being utilized in reality? It is not being utilized at, say, glycolysis, when glucose is being broken down. It is not utilized when we are saying, when we are moving our hand and all those things, right? There has to be a process where oxygen is actually required, and hence we are dependent on it, right? So that oxygen is required in the electron transport chain, because here oxygen acts as a terminal electron acceptor and gets converted into H2O, water. Okay, then ATP synthase is the proton gradient drives protons back into the mitochondrial matrix through ATP synthase, generating ATP from ADP. So what it basically means, that whatever the proton gradient was generated, this particular enzyme, which is called ATP synthase, it takes them in, because this proton was pumped where? It was pumped at the space between the two membranes. Remember that mitochondria is a double membrane structure, right? So in between these two spaces a proton is present. But imagine now the proton is too much in this space. So due to the concentration gradient, this proton would like to come inside the matrix again, right? But there is only one place where hydrogen or proton can come from the intermembrane space to the matrix of the mitochondria, is through ATP synthase. And this enzyme converts this proton or this energy into an ATP molecule. And till now, this whole process is for what? Energy generation. And the energy currency for living is ATP, that is adenosine triphosphate. Correct? This whole process, it's a very simplified manner, but if you can understand that where electrochemistry is being utilized is, all these complexes must have some element inside them in these proteins which will be able to receive an electron. Correct? Then only electron will be transferred, right? Just like when we were talking about galvanic cell, the anode and the cathode. The cathode was ready to receive the electron. The anode was ready to generate the electron, right? So if you have higher reduction potential, which means you can release electron very well, right? So if we talk about these complexes, first complex will be having ability to receive electron. This one will also have ability to receive electron. This will also have the ability to receive electron. But from where this ability is coming from? This ability comes from the elements. We have talked about, say, we have talked about zinc, we have talked about chloride ions, we have talked about silver, right? All these are elements at the end of the day, correct? So in these proteins also, the center is made up of some element, say magnesium, manganese, iron. All these things help in carrying electron from first complex to second to third and to fourth. Finally, when that electron is at the fourth, this energy is this electron then transfers to the oxygen. It converts that oxygen into water. But the electron which comes, the energy which it was being used, it was held in the form of transferring protons or hydrogen from inside of the cell or the matrix into the space between these two membranes. Due to the generation of this excess hydrogen ions or protons in the intermembrane space, this concentration leads to the generation of potential difference, or say concentration gradient. This concentration gradient can only be calibrated or can only be cleared from when these hydrogen ions or protons are allowed to come inside the matrix again. And how they can come inside the matrix? Only there is one opening in the inner membrane, which is called ATP synthase. Once this proton is traveling via ATP synthase, this enzyme will convert the hydrogen ion or the proton to form the ATP molecule, which is our energy. Okay, I hope that this is a little bit clear to you guys, that why we need to know about the ETC and electron transport chain overall with respect to the biological system. We'll see more about it whenever, like, there is, if I remember correctly, there's a question in which it is based upon the ETC only. There we'll try to understand more about the ETC reactions, or the electron transfer chain reactions, and the whole process as how it is taking place in more details. Okay, we can start discussing about the questions, but before that, there's little bit of information with respect to the ETC itself. So for this, let's talk about the ATP generation at the end of the day, right? That we are saying ATP is generated, but how much ATP is generated? That is also the question now. So each NADH, which means, so this NADH, if you remember, this NADH molecule, which is a small molecule which has the ability to transfer electron to complex 1, it was giving electron at complex 1. FADH gives electron to complex 2. Okay, so if we talk about NADH, it contributes to 2.5 ATP. If we talk about FADH2, it accounts for 1.5 ATP molecules. So the total ATP which we require, which is produced from one molecule of glucose, is 38 ATP, which means you had food. That food has different components. It has carbohydrates, lipids, proteins, right? All those things are there in the food. Take one component of that food, say carbohydrates, right? Carbohydrates have different types of carbs in it. Monoglycerides, polyglycerides, all those things are there. Now, from complex molecules, we cannot take out the stored energy, because where energy is stored, it is stored in the chemical bonds. So take carbohydrate. In that carbohydrate, take a monosaccharide. Monosaccharide means that it is made up of single type of carbohydrate. In that monosaccharide, imagine that monosaccharide is made up of only glucose. So if you have one molecule of glucose, this whole process of you having that food, you taking the regular breathing, inhaling and exhaling, during inhaling you are taking oxygen, that oxygen will go to break this glucose bond. How it will break that glucose energy bond? Because it requires energy. That energy is coming from the electron transport chain. Okay, so every single process is linked in this manner. So the overall conclusion for electron transport chain is that the ETC in mitochondria is crucial for ATP production via oxidative phosphorylation. It creates a proton gradient that drives ATP synthesis, making it an efficient energy harvesting process. Disruption in ETC by some either mutations or some external compound can severely impact cellular energy production. So I have one question for you guys. It's just a thought question. If you would like to attempt, it will be great, and if not, then it will be a thing for you to ponder upon. Imagine if second complex is somehow not working in the mitochondria, right? Either due to some mutation, due to some mechanical damage, or say some inherent disease, or some due to some drugs which you have taken and it has rendered complex 2 as non-functional. So according to you, what will happen if the complex 2 of ETC is not working or is not functional at all? Can you guys guess?
Even if the second complex is not working, there is still the gradient, concentration gradient is maintained.
Mm-hmm.
So this might again push the electron and take part in electron transport.
Okay. So you are thinking in the right direction, but just imagine there is a train for sake. Okay. So the first compartment is the engine. Then we have the first coach, second coach, and third coach. So from the engine, the first coach is not working. So engine is still able to pull. Okay, but the second connection is lost. So will the gradient be maintained if the second connection is not there connected to the engine? Will the engine be able to pull the third coach from its own? Because the connection is lost between the first and the second itself, right? So it will be difficult that the first complex can directly donate the electron to the third complex. Even if it somehow bypasses this, the whole process was to make a proton gradient. That proton gradient won't be there. And if proton gradient is not there, there won't be any protons in the intermembrane space. There won't be any concentration gradient. There won't be any push for the hydrogen ions or the protons to come from intermembrane space to the matrix from the ATP synthase so that ATP can be generated. Okay, so even with the limited functionality of any of the complexes, the whole ETS process will be disturbed, and at the end it will lead to the disrupted energy production. And the moment energy production is altered, our overall ability to work or function will be altered also. Now similar thing if we talk about with respect to galvanic cell, imagine there are two electrodes. Both of these electrodes don't have that much difference in their reduction potential. Electrons will still flow because the voltage will be maintained, the difference is there, but it won't be that effective. That effective means it won't generate that amount of energy. If energy is not there in galvanic cell or batteries, we talk about energy in the terms of power. That won't be more efficient enough to generate sufficient power to do the work at the end of the day, right? So the basic principle for the electrochemistry to work is to maintain a good potential difference, to make sure that electrons are flowing at the rate, it will again depend varying from one component to another component, and it it is spontaneous at the end of the day. Hence, instead of giving energy, we are taking out the energy. Okay, so this is just a basic introduction about the electronic transport chain. Now we'll begin with our okay, how to do this. How can I let participants finish automatically? Okay, we'll figure it out later. So we'll start with our question discussion for today. And I don't think so many of you were there since the beginning, and also I was muted. So this is the last class for this particular course. I hope you guys are up to date with the course material and you are registered for the exam also. Kindly mute yourself, whoever has joined recently. Yeah. Okay. So we gonna wrap it up quickly. We again gonna discuss the same process will be there. If there's a little bit difficult question, I'm gonna give you guys 1 minute to answer it. If it's a theoretical question or little bit like knowledge based question, I'm gonna give you guys 45 seconds to answer that. You can put your answer in the chat box. I will encourage you to like attempt these questions even if you feel like that you might not be right. Just attempting it, you might be right and you might be wrong. At the end of the day, it's not an exam. Okay, so feel free to attempt these questions, and these are pretty easy questions at the end of the day. So the first question is, in a lead acid battery, during discharge, oxidation takes place at the lead electrode, that is the anode, producing blank, whereas the lead oxide is reduced to PbSO4 at the cathode. So you guys need to tell me what is the half cell reaction for the lead acid battery, especially for the anode part. Okay, this is what it is asking, right? And your options are, first, that the anode reaction will produce protons and lead sulfate, or whether it will produce electrons, protons and lead sulfate, or it will produce electron, protons and lead oxide, or will it produce electrons and lead sulfate. I'll give you guys 1 minute for this question and your time starts now. I hope some of you might have attempted it. Let's check. Okay, electron and lead sulfate, option 4, that is electron and lead sulfate. Yeah, but we are forgetting about the protons. And why we are forgetting about the protons? Okay, how many of you have actually gone and seen the actual reaction which is associated with the lead acid battery? If I remember, I might be wrong here, but in the last class, I guess I have shown the very descriptive uh, explanation of these lead acid batteries with respect to the Nobel Prize when we are talking about lithium ion battery also. Okay, don't worry, we'll see it again here. I hope you guys can see my screen and is audible also.
Let's have a discussion on working principle of lead acid battery. This is very commonly used as storage battery or secondary battery. Before going through the working principle, we should know about materials used for lead acid storage battery cells. The main active materials required to construct a lead acid battery are lead peroxide, sponge lead, and dilute sulfuric acid. The positive plate of lead acid battery is made of lead peroxide. This is dark brown, hard, and brittle substance. The negative plate of lead acid battery is made of pure lead in soft sponge condition. Dilute sulfuric acid used for lead acid battery has ratio of water is to acid equal to 3:1. The lead acid storage battery is formed by dipping lead peroxide plate and sponge lead plate in dilute sulfuric acid. A load is connected externally between these plates. In diluted sulfuric acid, the molecules of acid split into positive hydrogen ions and negative sulfate ions. The hydrogen ions, when reach at lead peroxide plate, they receive electrons from it and become hydrogen atom, which again attack lead peroxide and form lead oxide and water. This lead oxide reacts with sulfuric acid and forms lead sulfate and water. Negative sulfate ions are moving freely in the solution, so some of them will reach to pure lead plate where they give their extra electrons and become radical sulfate. As the radical sulfate cannot exist alone, it will attack pure lead and will form lead sulfate. As positive hydrogen ions take electrons from lead peroxide plate and negative sulfate ions give electrons to lead plate, there would be an inequality of electrons between these two plates. Hence, there would be a flow of current through the external load between these plates for balancing this inequality of electrons. This process is called discharging of lead acid battery. Now we will disconnect the load and connect lead sulfate covered lead peroxide plate with positive terminal of an external DC source and lead peroxide covered lead plate with negative terminal of that DC source. During discharging, the density of sulfuric acid falls, but there still sulfuric acid exists in the solution. This sulfuric acid also remains as positive hydrogen ions and negative sulfate ions in the solution. Hydrogen ions, being positively charged, move to the electrode connected with the negative terminal of the DC source. Here, each hydrogen ion takes one electron from that and becomes hydrogen atom. These hydrogen atoms then attack lead sulfate and form lead and sulfuric acid. Negative sulfate ions move towards the electrode connected with the positive terminal of DC source, where they will give up their extra electrons and become radical sulfate. This radical sulfate reacts with lead sulfate of anode and forms lead peroxide and sulfuric acid. Hence, by charging, the lead acid storage battery cell becomes ready for discharging. Thank you.
Yeah, so you guys were right, but what you forgot to take in account that the solution which is present there is present in water. So water, due to the chemical reaction, will also release hydrogen ions, and that will be responsible for the reaction which is taking place at the anodic chamber. Okay, going to the next question. So read the following statements. Solid state ion selective electrodes. I hope, because these questions will only help you guys if you are following the lectures. Okay, so I really hope that you guys might have at least covered half of the lecture for this particular week. Okay, so solid state ion selective electrodes use a solid blank and ionically conducting substance, either alone or suspended in an organic polymeric material as the membrane. So if you guys have followed the lectures, you might know this answer, and it's like pretty straightforward. But still, I will give you guys 1 minute for this particular question. So the question basically is asking that in the solid state ion selective electrode, the solid, which is the electrode, is basically made up of what? Okay, so whether it's sparingly soluble, insoluble, in a supersaturated state, or in melted form. Your 1 minute starts now. Try to attempt this. And even if you have not followed the lectures, try to answer it based upon the name which these electrodes have. Your 1 minute is about to get over. Yeah, it's done. Let's see if anyone of you have attempted it. Oh, where it went. Okay, sparingly soluble, option 1. Oh, you guys are following the lectures. Great. So, also, it was a pretty easy question to answer, right? But still, we'll see. Again, I select this video so that you get an alternative perspective also with whatever you are seeing in the current lectures. Okay.
The second and more common type of indicator electrode that's used is an ion selective electrode. And I have here an image from the online textbook that shows sort of a general schematic for ion selective electrodes and how they work.
Audio is not.
The heart of an ion selective
Audio, we couldn't hear the audio. We can see the presentation.
Even in the earlier one.
Video, yeah, ma'am. In the earlier video, so audio was not possible.
Okay. Oh, this is troublesome then, because I have, even in the last session I have shared in this way only. Oh my god. Okay, let me check quickly, because we don't have that much time, even you guys don't. So, audio setting, microphone, default speaker. Ideally it should be there for you guys because I've shared the screen. Let me stop and start sharing again. Okay. Are you guys able to hear it now?
electrode is down here at the bottom, this ion selective membrane. And this membrane
No, ma'am. But okay,
No,
captions can
I'll
be.
try one more time. Yeah, I that is one of the reason I'm skeptical about turning on the captions. Just give me one more try. Otherwise, we'll continue, because this is a little bit um uncomfortable to just keep watching the video and not hear what the presenter is saying. So just give me 1 minute. This time I'll try to share one window at a time.
can be made out of many different materials, and so this discussion we're going to have here is going to be general.
Can you hear?
And then we'll start.
No, ma'am.
Okay, I'm sorry, but yeah, these slides will be uploaded and these links will be there. this time. Okay, but I don't know why this is there.
Looking at some of the specific ways you can construct these ion selector electrodes. So the first type of ion selector membrane that was discovered is actually glass. This is what's used for a pH electrode. There are also other types of solid crystals that are used as this ion selector membrane. So for example, the chloride ion selector electrode we've used in lab uses this. Other halide, including fluoride and others, use the same type of membrane. And there are also liquid-based membranes. I'll put liquid in quotes because, of course, it's not an actual liquid because then it would flow off of your electrode. But these liquid-based membranes are another type of ion selective electrode that's used. And so we'll talk about each of these. But let's talk about, first of all, the general picture of what's going on here that'll apply to any of these types of membranes that are specifically used. So the ion selective electrode is made out of two reference electrodes. So we have one on the inside of the electrode and one on the outside that goes into our sample solution. And the purpose of these is that we'll have our measured potential, so we measure on a potentiometer, is going to be the difference between our reference electrode on the sample side minus our reference electrode on the inside of our potentiometer. Then we'll, of course, measure a junction potential. And importantly, we'll measure what the potential is across this membrane. And so everything else, so these first three values will be fixed, ideally, right? So these shouldn't change. Now, that's the whole point of a reference electrode, is that its potential doesn't change. So either our inside or outside reference electrodes, those should stay the same. And the junction potential should stay the same even as concentration of our sample changes. But on the other hand, the potential of the membrane, this depends directly on the activity of the sample. And so we can write out an equation to represent this. E membrane will be equal to some, now we don't have a standard potential for the membrane, but we'll call this E asymmetric, minus, and we can write out like the next equation, 0.5916 volts divided by N. Now this, of course, is assuming that we have 25 degrees Celsius temperature, right? All the usual substitutions that go in to get this number here, times the log of the ratio of our activity on the inside and our activity on the outside. And this ratio is what matters. Now, what we can do in this is that this internal solution, right, this right here, let me pick a different color you can actually see. Let's do red. This right here, this internal solution, we control this concentration. And it's fixed. So this is going to be a constant. This E asymmetric, this ideally is zero. Basically, when the internal and external activities are equal, there should be no potential across the membrane. In practice, that's not the case. There's usually some asymmetry here. But that's a fixed value. That's just a number. And so what we can see is that overall, we're going to have E measured, I'm going to lump a lot of things together, will be equal to some constant we'll call K here, minus 0.05916 divided by N volts. And K takes a lot of stuff into account, we'll talk about in just a second, times the log of the activity of the outer solution, or what's called a sample in the figure. Because everything else is fixed, we can lump, right, this term here, the reference electrode, the other reference electrode, the junction potential, this E asymmetric, as well as, we can sort of factor out this internal.
Okay, they are just trying to solve the Nernst equation for this. This is just an example of how you can use this equation, because we are following this equation since the beginning, right? So we can fit this equation for a basic galvanic cell, for a solid state type of cells, or for lead acid batteries, for anything, because at the end of the day, the components which are there in the Nernst equation are the components or the basic principles in all of these batteries. I'm not completing that video, so most likely just after the this our discussion for today, I'm gonna upload this video as soon as we are done with our discussion today, so you guys can go there, and then also you can see this whole lecture again, and there the audio of that video will be available. Okay, because I guess I have 2 3 more videos with related to the questions which we're gonna discuss. I prefer this method of knowing things, because when you see a video and you see the real life application of these things, understanding becomes easier. Because if I see, the lectures are teaching you concepts, I am trying to refine them, and once you see the application of the similar things, it becomes very real for understanding. Okay, hence I have so many videos in my lectures, which ensures that you can have a wholesome knowledge of particular thing. The next question for today is, in the case of a lead acid battery, the cell potential is about blank, and is a typical 12-volt car battery is composed of 6 cells connected in. It's a generic question and also sort of basic knowledge question. If you know what are the differences in serial connections and parallel connection, you can try attempting this question. Okay, I'll give you guys 1 minute for this particular question, and then we'll see what exactly and how exactly a car battery works. Okay, your time starts now. So, any of you tried attempting it? See what it says. Oh, great. All of you are following the lectures, then you guys don't need me at all. Great, kudos to you. And yeah, it was pretty easy question to attempt, right, at the end of the day. But this particular video is interesting. We're not going to follow it throughout, like till the end, but it's a pretty long video, and also you guys are not able to hear it. We'll see till the basic components are covered. Okay.
The 12-volt lead-acid car battery. These large and fairly heavy batteries are used in every combustion engine vehicle on the planet. They're an essential part of the vehicle. So, what does it do and how does it work? That's what we'll be covering in this video, which is sponsored by Squarespace. Head to squarespace.com and domains. The 12-volt car battery looks something like this. This is a lead-acid battery. We call it a lead-acid battery because inside the unit are lead plates, which are submerged into an acid. This creates a chemical reaction, which releases energy and provides us with a voltage and current. The battery is therefore storing energy in the form of chemical energy. It does not store electricity. This chemical energy is converted into electrical energy whenever we need it. This battery is also rechargeable. If we supply the battery with electricity, then we can reverse the chemical reaction and recharge the battery. These types of battery provide large amounts of current, especially compared to the typical smaller household alkaline batteries. We have covered how alkaline batteries work in our previous video. Do check that out, links can be found in the video description down below.
Are you salaried and planning to buy a term plan? Here
The typical car battery is found in the engine bay of the car. The battery is first used to start the engine, and it does this by providing electricity to a small electrical motor known as the starter motor. The starter motor engages a small gear onto the flywheel of the engine. It turns this to turn the crankshaft, which starts the combustion engine. The small gear then disengages and the engine runs by itself. The starter motor needs to provide a huge amount of force to be able to turn the flywheel. So the starter motor will draw an extremely large current, possibly hundreds of amps, but this is only for a few seconds. This large current demand is going to reduce the energy storage of the battery, so we will need to top this back up. Connected to the engine is an alternator. The alternator is rotated by the engine, and as it rotates, it generates electricity. This electricity is fed back into the battery to recharge it. While the engine is running, the alternator recharges the battery, but it also provides the electrical power for things such as lighting and the music system. When the demand for electricity in the car exceeds what the alternator can provide, then the battery will provide this additional power, which again drains the battery. If the engine is switched off, the alternator stops rotating and recharging the battery. So the battery will provide the full electrical power to the car until it's dead. At this point, the battery can't provide enough electricity to start the engine, so we will need to jump-start the car. Let's have a look at the main parts of a car battery and then we'll understand how it works. First of all, we have the plastic case which holds all the internal components in place. On the top, we have the plastic lid, and there are two terminals, a positive and a negative. By removing the lid, we can see inside. Notice the casing is divided up into 6 separate chambers, each separated by a plastic wall. Each chamber is known as a cell. Each cell generates around 2.1 volts of DC or direct current. Each cell is connected in series. The negative of one cell is connected to the positive of the next cell, to give us a total voltage of around 12.6 volts. It's the same as if you connected household alkaline batteries together. The voltages add together to provide a higher total voltage. Each cell in the battery is connected via a plate strap. This is made from lead. These straps are welded together through the plastic wall to form the connection. As we look at the battery from this view, we see that current flows through the battery cells from the positive to the negative, and that's using conventional current theory. But what's actually happening is the electrons are flowing in the opposite direction, from the negative and to the positive. But we'll cover that and you'll see why a little later in this video. Notice there are 2 plate straps in each cell, one positive and one negative. These are called plate straps because each strap is connected to a number of plates, which are sheets of lead. The plates are formed into grid-type structures, which maximizes the surface area. The grids are coated in a paste of lead oxide. The paste is where the chemical reaction occurs, and we'll see that a little later in this video. The paste acts a bit like a sponge and is going to absorb some of the electrolyte liquid, which improves the battery performance. The size of the plate determines how much current a battery can provide, but it doesn't change the voltage. The materials used for the chemical reaction and the number of plates determines the voltage produced by each cell. The grid holds the paste in place to ensure a uniform current distribution across the plate and helps to transport the electrons out of the battery and around the car's electrical circuit. The negative plate is the anode, and this is a plate of pure lead, although some small amounts of additives are added to harden the lead and protect it from corrosion. The positive plate is the cathode, and this is made from lead oxide. The plates are made of dissimilar materials to form the chemical reaction and release the electrons. Now, we don't want the positive and the negative plates to come into direct contact with each other, because this would short-circuit the battery. So, instead, we place each positive plate into an envelope separator. This is just a porous material that allows ions to flow through it without the materials coming into direct contact with each other. The positive and the negative plates will sit between each other with a small gap in between each plate. The chamber is then filled with an electrolyte liquid of sulfuric acid and water. Hence, the battery is called a lead-acid battery.
Hey, have you heard of NumPy?
So I guess you guys get an idea exactly what a car battery looks like. It's pretty cool because if you remember our discussion in, I guess, second lecture itself, we were talking about voltaic pile. So you remember in that the anode and the cathode were piled up against one another, and then there was some cartridge or a cotton or some cloth which was dipped in an electrolyte. So from there to how compact our batteries are, it's a great uh, progress in the field of batteries. Okay, and we I don't have to tell you guys how important it is to keep the innovation going on in this particular sector so that we can have more efficient and more refined batteries, keeping the sustainability also in our mind. Okay, so the next question for today is: a blank potential can develop when a metal electrode comes in contact with a solution containing its cation. Is it a pseudo potential, a synthetic potential, a junction potential, or a contact potential? I'll give you guys 1 minute for this particular question, and your time starts now. Even if you don't know the correct answer, try to understand the question and then try to fit these potentials, that what exactly we are trying to ask here, we're trying to answer here. So it's the junction potential. We'll discuss this, that what exactly a junction potential is, little bit background information about junction potential. Okay, but you guys already know, but let's just have the verbose about it, that what junction potential is, and then we'll try to understand it in a better way. So junction potential is the potential difference that develops at the interface between two different electrolyte solutions or between two dissimilar ionic conductors. It arises due to the unequal mobility of ions in a solution when they diffuse across the junction. What are the causes of junction potential? First one is different ionic mobilities. Ions in solution have different diffusion rates. For example, in a salt bridge, if one ion moves faster than the other, a potential difference arises. Concentration differences, which we saw in the ETS, okay? If two solutions of different concentration come in contact, ions will diffuse at different rate, creating a potential. Electrolyte interface, it is when two different electrolyte solutions meet, selective ion migration lead to charge separation and hence creates the junction potential. Some of the examples of junction potentials are liquid junction potential, which is it occurs in electrochemical cells, example at the interface of two different solutions in a salt bridge. Or second one is membrane potential, as we discussed in the last session as well as somewhat in the current session. A biological example where ion gradients across cell membrane generate an electrical potential. Okay, some of the experiments which impact junction potential are: junction potential can affect electrochemical measurements, leading to errors in pH measurement and electrode potential, because at the end of the day, what they are not giving us the ideal result what we have calculated by Nernst equation. Okay, so there is little bit non-compliance with the thing which we are calculating and what is actually happening. Second is in electrophysiology, it must be corrected to obtain accurate membrane potentials, which will help us to come up with more accurate and more efficient sensors and biochemical or biomedical devices. Okay, let's see a little bit more about junction potential.
In this video, I want to introduce the concept of the junction potential. If we have two solutions, for example, that are connected to one another, and let's say that one solution is rich in sodium chloride, and then the other solution is just plain old water. We've got sodium ions and chloride ions that are going to diffuse from the high concentration over to the lower concentration. If we take a look at what I've written over in this left-hand side here, it's the mobility of some ions. The mobility is in units of meters squared per volt second. The units are not important at this point, but just the values are. And if we take a look here at sodium versus chlorine, it looks like chlorine, or the chloride ion, is more mobile than the sodium ion by upwards of, maybe 20% or so. So that means that if we take a close-up view of what's in this region right here, what we will find is that the chloride ions are going to move faster than the sodium, and we're going to set up a region where there is a positive charge, because that's where the slower sodium ions are, and a region of negative charge where the chloride ions are. This separation of charge creates a small electric field, and this is called the junction potential. Now, one question might be, why do we care about this? And let's go ahead and draw down here a typical galvanic cell, where we would have two electrodes. What they are aren't important at this moment. Connected with a voltmeter, and remember that we've got this salt bridge right here. So we've got two solutions, solution spilling over a little bit. The junction potential is going to be important right in this region and also right in this region here, because the salt bridge, let's say the salt bridge might be KNO3, potassium nitrate, and the one solution here might be copper nitrate. And the solution here may be zinc nitrate. Now, since we have nitrates in as all of the anions in this particular case, the anions are not going to contribute too much to the junction potential, but potassium ions and zinc ions and copper ions will all travel with different mobilities. So there will be some charge separation in these areas here, possibly because the zinc ions could travel more slowly than, say, the potassium ions. This potential, this junction potential, is going to show up right here. This potential will also show up right here. So the potential that we think we're measuring, which is just the reactions between this half-cell reaction and this half-cell reaction, will also have contributions from the junction potentials. And so the value that we measure will have some uncertainty due to the junction potentials. How much uncertainty are we talking about here? Well, if we have, for example, 0.1 molar hydrochloric acid, and that is in connection to 3.5 molar calcium chloride, then the junction potential in these cases is going to be around 3.1 millivolts. We don't need to know how this number is calculated at this point. If we are measuring the pH and of the solution, and maybe there's a junction potential of 3.1 millivolts, say, because of the internal solution of the pH electrode, it has a pH response of 59 millivolts per pH unit. This 3.1 millivolts is going to result in an error of 0.05 pH units, or about 12% of the hydrogen ion concentration. So we do need to be careful or be aware of junction potentials, because they can contribute a significant amount of error to the observed measurement.
You guys got an overall idea, right? So this is the first time I'm not completing all the videos because you guys can't hear it. So hopefully the moment we are done with today's discussion, as I have mentioned earlier, I'm going to upload this particular session recording, and you guys can see it there. And within one day I'm going to upload this slide also, so that you yourself can access these particular links. Okay, so the next question for today is, when a cell contains a boundary between two electrolytic solution of different composition or concentrations, a blank is developed due to the diffusion of the various components at characteristic rates in the boundary zone. You guys already know this answer, and we have seen in the previous video sessions also. So I'm going to give you guys 45 seconds for this particular question, so that you can answer in the chat box. I'll read that again for you. So the question asks, when a cell contains a boundary between two electrolytic solution of different compositions or concentrations, a blank is developed due to the diffusion of the various components at characteristic rates in the boundary zone. Is it a solid potential is developed, or pseudo potential is developed, a liquid junction potential is developed, or nurse potential is developed? Your time starts now. So obviously the right answer is, let me see how many of you tried to attend. Nernst potential. Okay, well, I should have played that video to the completion. As you can see here, we are talking about the differential movement of different electrolytic solutions. This question itself indicates that we are talking about the different solutions. Either they are different solutions or they are similar solutions but in different concentration, which means that the ions which are present in this solution will move at differential rate and they will create a liquid junction potential. Okay, and if you guys have trouble, we can have an extra class maybe after 20th where we can discuss about these potentials in detail. Otherwise, you can go back to the session classes which Professor Manik Das has taken, and you can like clear your concepts there itself. It is completely on you guys. So the next question is, read the following two statements. Electrochemical signals from metalloprotein can be detected as a continuous analog signal generated by the reduction and oxidation of metal ions in the structure when a redox potential is applied. Second, these reactions in metalloproteins are more effective than other physical and chemical reactions because they are already optimized for transferring energy and mass in natural biological systems. So what it is asking, so it is, this particular question is asking that we have read these two statements. We need to tell whether both the statements are false, both the statements are true, or statement 1 is true or statement 2 is true. So we need to answer this. If you guys, again I'm gonna repeat myself, if you have followed this particular week's all the lessons, you'll be able to answer this because it was discussed in quite detail. And your time starts for this particular question starts now, and the time is 1 minute. Okay, try to answer it, go through these statements thoroughly once, and even if you don't know which is the right answer, try attempting it. Your time is about to be over. Try attempting it. And the time is up. Let's see how many have tried. Okay, oh, okay, you corrected your answer. Option 3. So option 3 says statement 1 is true. I'm not gonna discuss much with respect to this, but yeah, option 1 is obviously true. The option 2 states these reactions in metalloprotein are more effective than other physical and chemical reactions because they're already optimized for transferring energy and mass in natural biological system. So this is a direct example of the electron transport chain which we just like studied very briefly in the beginning of today's session. We're gonna see a more detailed electron transport chain, and we'll see that the proteins which are incorporated in the membrane for like complex 1, 2, 3, 4, in between them also there are small molecules which help in electron transport from one complex to another complex. These proteins are majorly, they have a metallic entity associated with it, so they are already optimized in the nature for performing such functions. So it was indirectly related to that process itself. And some basic details about the electrochemical signals in metalloproteins. So the detection of electrochemical signals in metalloproteins. Metalloproteins contain metal ions that participate in redox reactions. When a redox potential is applied, these metal centers undergo electron transfer reactions, which generate an electrical signal or electrical current that can be detected as a continuous analog signal. Oxidation reaction and reduction reaction, majorly if we are talking about in the like general terms, we can see that in the oxidation, the iron will be oxidized, and in the reduction, it will receive that electron. The redox cycles create a measurable current that varies depending on the redox state of the protein and at the end at the element or the molecule particular element which we are using in the protein. Okay, so some of the examples of metalloprotein includes cytochrome C. It is a metalloprotein containing heme iron that undergoes redox transition, generating the signal. Blue copper proteins, they are also there in the nature, which the copper is there and the redox reaction takes place as stated here, but with respect to copper. And why metalloprotein reactions are more effective? Because metalloproteins are optimized for efficient energy and mass transfer because they have evolved to perform essential biological functions, right? This makes their redox reactions more effective compared to the artificially synthesized redox active molecules, because it is the thing which we are synthesizing. Correct. As you understand, even the standard hydrogen electrode which we have, we are assuming that their reactivity will be 1, right? But in reality, it is not there. But if we talk about metalloproteins, evolution and like millions and millions years of evolution have put that particular element in a protein, which means it has already optimized for the best function that protein can perform with that element associated with it. Okay, so few reasons for the higher efficiency of metalloproteins include optimized electron transfer pathway, selective binding and transport, coupling with biological pathways, redox tuned active sites, electron transport chain, as I have mentioned earlier, and we'll see what it is exactly. So the overall conclusion is metalloproteins naturally facilitate highly efficient electron transfer due to their biological optimization. Their redox activity can be electrochemically detected as a continuous analog signal, making them useful in biosensors, bioelectronic devices, and understanding biological electron transfer mechanism. Now we're gonna see exactly how electron transport looks like and how it functions.
All eukaryotic cells, from yeast to those that make up the human body, contain membrane-bound organelles with specialized functions. Mitochondria are double-membraned organelles that harness most of the energy that cells need to grow and reproduce. Nearly all of this energy comes from reactions that take place at the inner mitochondrial membrane. One of the key roles of this membrane is to act as a barrier to positively charged particles called protons, thus allowing a concentration gradient to be maintained where the intermembrane space has far more protons than the matrix. The membrane also contains a large protein complex called the F1-F0 ATP synthase, which uses the proton gradient to drive the synthesis of ATP molecules. These ATP molecules ultimately provide the energy for most of the cell's reactions. Just as man-made power plants produce electrical energy by using the flow of wind, water, or steam to rotate a turbine, the synthase makes ATP by using proton flow from one side of the inner membrane to the other to rotate protein subunits. If there is no proton gradient, synthase subunits stop rotating, and the cell can quickly become starved of energy and die. Therefore, the protein complexes and small molecules that establish this gradient and maintain it play an essential role in the life of the cell. At the heart of this system are 4 protein complexes, numbered 1 through 4. Complexes 1, 3, and 4 directly pump protons from the matrix into the intermembrane space. Complex 2 does not directly pump protons, but it does promote proton pumping in complexes 3 and 4. Proton pumping requires energy, and the 4 protein complexes get this energy by transferring electrons through a series of coupled reactions. This linked process of electron transport is why the 4 complexes are collectively referred to as the electron transport chain. Let's focus on complex 1. A byproduct of sugar metabolism called NADH deposits 2 high-energy electrons in complex 1, where they are passed along a chain of redox centers. Redox centers are clusters of atoms that have different affinities for electrons based on their unique atomic configurations. Let's closely consider a pair of redox centers to reveal 2 reasons why an electron moves from the top redox center to the bottom. First, the bottom redox center has higher affinity than the top one. Second, the distance between these adjacent redox centers is ideal for an electron jump to occur, which explains why electrons typically don't bypass the bottom redox center. A small amount of energy.
See, you can see how well it is optimized, right? And hence metalloproteins are the core reason that they are very efficient in the biological system. And by learning these principles, we are trying to replicate the same information by generating artificial systems. Okay? I guess you guys can see this later itself, as I've mentioned, because you cannot hear it. It's pretty uncomforting to just like see the video and not hear it. Okay, I'm making sure that I'll upload this video as soon as we complete our discussion today. The next question is,
Ma'am, can we stop over here, ma'am?
I think I just have 2 more questions to discuss, and also as this is the last class, I have to complete it.
Because I'm in a position to leave.
Oh, okay.
That's what, ma'am.
Okay, let me check. I think I have 3-4 more questions. As today is the last discussion hour, then these questions won't be discussed. So, and if you want, I can just discuss these questions and upload the video as well.
Okay, ma'am.
Yeah. So just give me 5 more minutes. There are 3 questions left. I'll quickly go through them. Okay.
Okay, ma'am. Yeah.
In blank, when Junger describes the first nickel iron and nickel cadmium batteries, these alkaline batteries became predecessors to the later nickel metal hydride battery commercialized in 1989. Obviously, it's a theoretical question. You won't be not necessarily be having this number at the top of your memory. It's a general knowledge question at the end of the day. This is the basic history which I have given for the nickel iron batteries, and it's a pretty interesting history to read about. Okay, so the information is there. The next question is, with atomic number of 3, as we all know, lithium is the lightest metal with a density of only. So I really hope that you guys know this. I'll give you just 30 seconds to answer this question. If you know, you know, because again, it's not a thing which you'll remember at top of the head if you are not regularly solving the questions, right? So the right answer is 0.53 gram per centimeter cube. Here I have given the basic details and the density of these alkali metals specifically, which is the group 1 elements. And if you want to know how the density is being calculated, then or what are the properties associated with the these alkali metals. I have given a very 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 brief things about this, and if you want to know more, just you guys have to let me know whether you want an extra class or not, okay, in the coming or next week. The standard potential of calomel electrode is this. You have to answer because it was thoroughly discussed in this week's lecture. So calomel electrodes, what is the standard potential which they offer? Can you give whether is it plus 0.26 volt, plus 9 volt, plus 0.62 volt, or minus 0.9 volts? Anyone who is like planning to attempt this question? 0.53. Oh, you have answered for the last one. 0.268. The correct answer is yes, plus 0.268 volts. And again, I have the associated video right here, but as the person who is in this particular session, due to the time restriction and time constraints, I might not go into it, but every single detail will be in the slide as well as in the session which I'll upload, like this same session I'll upload. The last question for today is, the standard reduction potential of all redox couples is defined relative to blank reference half cell. Yeah, so this is an interesting one. It was also discussed in this week's lecture. So the standard reduction potential of all redox couples is defined relative to which half cell reaction? Fe3 plus to Fe2 plus, H plus to H2, PT or AU? Anyone wants to attempt? H plus, oh, okay, I know where the confusion is. You said this because of the SHE, right? Standard hydrogen electrode or reduction potential. But remember, one of the drawback is that in reality you cannot use this. Theoretically it's okay, experimentally also it's fine, but practically it is not possible to carry hydrogen gas with you, right? So in real life, in practicality, we use iron as the reference electrode to measure the redox reactions. Okay, so I'm sorry for the rush in the end, but yeah, thank you so much for attending today's session, and feel free to reach out to me if you need any help, any suggestions, any study material. I'll upload this session, and even with not respect to this particular subject, if I'll be able to help you out, I will. So thank you so much, and all the best for the exam. Thank you.
Thank you, ma'am.